This painter is working hard even as he climbs the ladder. He's doing work on his body as he lifts it up the ladder. These learners are also working hard. Even though the learners have a short break in their lessons, they are working hard against the force of gravity as they walk upstairs to their next lesson. He pushes the child uphill in the go-kart. He works against the weight of the child and the weight of the go-kart. Even at the gym, people work hard as they take time to exercise after a day at the office. Lifting weights gives your body a good workout. Hello, I am Keke. Welcome to the third lesson in this series of lessons on gravity and mechanical energy. In our previous lesson, we found that the meanings of words in physics and everyday speech are not always the same. In everyday speech, the words mass and weight are used to mean the same thing, but in physics, these two words have very different meanings. In today's lesson, we are going to examine another word, the word work. By the end of today's lesson, you should be able to explain the relationships between workforce and displacement. At school and in industry or commerce, the term working hard has different meanings to different people. You may reckon that you are working hard, but your teacher may hold a different opinion. Working hard at studying or producing the goods is much more an opinion held by the worker and his colleagues, or an attitude to the job than something that is easily measured. The good news in today's lesson is that in physics, we can actually measure and quantify the amount of work done on a body. Work done can be related to force and displacement. Let's have a closer look at these terms. We will start with force. We use the word force to mean a push or a pull on an object. This boy pushing the car is applying a force to the car. Notice, at first the car is not moving, but when he gets some help, the car moves forwards in the direction of the force. A force can be applied by directly touching an object or by using some other material attached to the object. This type of force is called a contact force. When this mass piece is attached to a spring, a force can be applied by pulling the spring. Notice that while the force is applied, the spring stretches. But not all forces are contact forces. Some forces can act on objects at a distance without directly touching the object. These non-contact forces are due to a force field. Can you name 3 common force fields? Remember, there is a magnetic force field around magnets, an electric force field around charged objects, and a gravitational force field around any object that has a mass. There is one final thing to remember about forces. Forces always act in a particular direction. That means force is a vector. When we think about force, we must state the direction it is acting in. Now that we've had a brief look at forces, let's recap on the meaning of the word displacement. Do you remember what this word means? Why don't you explain it to someone or write down a brief explanation? To describe motion, the first thing we notice is that an object changes position. It moves from one place to another. We call the change in position from the start to the end the displacement of the object. When we measure the displacement of the object, we measure the change in position between the initial and final positions in a straight line. So, when we state displacement, we must always remember to state the direction too. We can indicate the direction using compass points, by using the words forwards, backwards, up or down, or by using a sign to show the positive or negative direction. Now that we have a good idea of the terms force and displacement, let's have a look at some situations where real work is being done. Look out for the combination of force and displacement. The go-kart is pushed along a horizontal road. The boy applies a force onto the go-kart, which causes it to be displaced. He is doing work on the go-kart. Watch this ball falling. It has clearly been displaced, but is there a force acting on the ball? Of course there is. The weight of the ball is the downwards force. It is this force due to the gravitational field that causes the ball to be displaced. We say the gravitational field is doing work on the ball. Notice that in both these examples, force applied and displacement have the same direction. Work is done when force moves an object through a displacement in the direction of the force. Now, let's think about how the force applied and the displacement of an object are related to the work done on the object. If we are going to measure work done fairly and not depend on opinion, we need to set up some experiments. Let's go to the lab.
Hey there guys, have a look here. I've got mass pieces of different mass. I've got a spring balance, which is going to be used to measure the force applied. And I've got a meter rule. Now we're going to do some work with these mass pieces here by attaching the spring balance here and measuring the force applied and the displacement. Now in this experiment, I'm going to keep the displacement constant at 1 meter, which is why we have a meter rule. Now remember, always, always, always write your data in a table when you're doing experiments. Now our displacement is going to be constant at 1 meter. Right. Let's pull the first mass piece across the table and measure the force applied. Attach the spring balance nicely there. Going to pull it across the table, 1 meter. There we go. And it gives a reading of 0.2 newtons. Now watch what happens when I pull the next mass piece. Again, it's at a constant displacement of 1 meter. There we go. Pull it across. Very interesting. The reading is 0.4 newtons. Now it's very obvious that the force applied on the second mass piece, which is slightly bigger than the first one, is going to be more than the first mass piece. So where do you think I applied more work? You can try this yourself by lifting objects of different mass to the same height. And remember that the force you apply to an object is actually equal to the weight of the object. I think you'll agree with me that when there's a greater force applied, more work must be done. In fact, work is directly proportional to the force applied. But what about the effect of displacement?
In which case is more work done? In case 1, when a force displaces a block through half a meter, or case 2, when the same force displaces the block by 1 meter. I think it's very clear. To be fair, more work was done when the block was moved further. So when the displacement is greater, more work is done. In fact, work is also directly proportional to the displacement of an object. We could express these relationships by using the equation. Work done, W, equals the force applied, F, times the displacement of the object, S. Now that we know how work done is related to force and displacement, let's look for any other quantities that can be related to work. When we watch people doing work, it certainly uses up energy. Maybe there's a link between work done and energy. In the 19th century, James Prescott Joule thought that work must be related to energy. He carried out many experiments to show this relationship. He found that whenever work is done on an object, energy is transferred to it. To honor James Prescott Joule, the SI unit of work and of energy is now defined as a joule. The symbol used is a capital J. 1 joule of work is the work done when a force of 1 Newton causes an object to be displaced by 1 meter. So 1 joule is equal to 1 Newton meter. When calculating work done or the energy transferred to an object, we do not give direction in our answer. Work and energy are not vectors, but scalars. There are 2 types of energy that we'll consider in this series. Potential energy, which is stored energy, and kinetic energy, which is the energy of motion. The sum of potential energy and kinetic energy is called mechanical energy. Now let's calculate the work done on the go-kart and see if we can identify the type of energy transferred. Remember, a force of 50 Newton is applied to the go-kart. The force causes it to be displaced by 5 meters in the same direction. Can you find the work done? Compare your answer with mine. I have substituted the values for force and displacement into the equation and find the work done is 250 joule. So we can say the boy transferred 250 joules of energy stored in his body to the go-kart. What type of energy does the go-kart now have? Well, the go-kart is moving, so it must have kinetic energy. Now, I want you to do a similar calculation for your task. Calculate the work done by the gravitational field when a ball with a mass of 250 grams falls from a height of 15 meters above the ground. That task may seem a little tricky, but there's a hint to help you. Remember, the SI unit of mass is kilograms. Also, mass is not a force, but weight is. Remember, you can check out the suggested answers to all the tasks by going to our website. Do join me for our next lesson when we will discuss the energy transfers that take place when work is done. Goodbye.